So hello friends, welcome to my channel. I'm in coaching center. Today I'm going to explain your 10th standard science chapter 13, magnetic fields and electric current. So let's come to the chapter. So needle, we saw compost needle deflects. Compost needle deflect when passing current. When current is passing current, the compost needle deflect. This is because, so we can say that electric and magnetic or magnetic or magnetism are linked with each other. Linked electric and magnetism are linked with each other. With each other, they are linked. We can say. So in this chapter, we learn about. In this chapter, we learn about. We learn about magnetic fields, electromagnet, and other topics we learn in this chapter. So let's come to the magnetic field first. Magnetic fields. So a small bar magnetic fields, a small bar magnet deflects. So what happens means a small bar magnet that has ends, the ends of the that are that has ends or placed, the ends of that are placed near compass. If it is placed near compass, the both ends that are north, the both ends, the north pole and the south pole, the north pole and south pole of the magnet and south pole of magnet, there are both ends. So if they both are putted, we can say both are putted in a compass, and to the both ends of the bar magnet there are some iron fillings. You can see they are attracting them. In this you can see. So the force that are surrounded, the force that is surrounding or surrounded not surrounding a magnet, the force that is surrounding a magnet, in which the force of the force that is surrounding the magnet, in which the force of the magnet can be detected. We can say that this magnet has this much force, it will attract this much, that is called as the magnetic field. This is the explanation or the definition of magnetic field. They may ask the definition of magnetic field for 1 marks. So the lines, see there are lines in this photo, in this magnet. The lines, they are saying, they are representing the lines, they are representing the iron fillings, or the iron fillings, not the magnetic fields. They are representing the magnetic fields, the lines. This image you can, by as you are seeing, see here there are lines, they are coming, they are like magnetic field means the lines here. In this you are coming, see here, line, one circle like small they are there. So by this we can say there are some force is there that are attracting the iron fillings and making it in that shape. So this was example or a explanation or definition for magnetic field. You have to write the definition of magnetic field if they ask. And the next topic is quantitative field is quantitative quantity magnetic field quantity that has both direction and magnitude. It has both direction and magnitude. So there is emerge from north pole to south pole, north pole to south pole, as you know. And the field is stronger, the magnetic field is stronger. The field is stronger, it is very little bit stronger. The field is stronger. So magnetic field, next is magnetic field due to current carrying conductor. The magnetic field due to current carrying conductor. This is a simple circuit in which a straight copper is placed parallel to over a compass needle, and the deflection of the needle becomes opposite when the direction of the current is reversed. You may see here it was from north and south, and now it becomes so here no south and north. This is because the current is force of current is, or the current is changed. So it also changed. And next is magnetic field. The next is magnetic field due to a current through a straight line. The magnetic field straight line conductor. The magnetic field due to a current is our next topic. So we shall first consider magnetic field around a straight line. We should first consider that. So first we will consider that. Here also an image of a pattern of concentric circle indicating the fields on the magnetic fields. So to see the current vary. So what means to see the vary of current in a wire, to see the vary of current in a wire, we need to find the deflection. Find the deflection in the magnet. Deflection, then we can say whether it is varying or not. If current is increased, the deflection. If current is increases, then deflection also increases, because more current is going, means deflection also gets more. If it gets decreased, then it also gets decreased. So thus the magnetic field produced by a given current in a given conductor in a thing, the magnetic current produced or magnet it is there, conductor decreases in a distance, decreases in a distance, it decreases, the current decreases in a distance from it, increases. If distance is more, it decreases. So right hand thumb rule. First, next is right hand, right hand thumb rule. So what is this right hand thumb rule? Well, I will say what is this right hand thumb rule. So this is an image of right hand thumb rule that is given in your textbook. So this is magnetic field that is around the thumb, and this is current coming from up to down. So you imagine that imagine you are holding a current carrying conductor, holding a current carrying conductor. Imagine you are holding a thing that is carrying current carrying conductor in your right hand. You are holding that right hand. Such it should be such that the thumb should be in the direction of the current. That thumb should be in direction of current, such that, and the finger should be wrapped. You should feel that the finger should be wrapped. You should feel that his finger is wrapped with magnetic field. It is wrapped with magnetic field. You should feel that. Then that is known as right hand thumb rule, and the current is going from up to down. And also magnetic field due to current and magnetic field due to current through a circular loop. In a circular loop, the magnetic field, how it works, let's know about that also. So this is magnetic field in the loop. So we saw right hand thumb rule, thumb rule and magnetic field around the current we saw. So we know that magnetic magnetic field, the magnetic field that is produced by a current carrying straight. So we can say that the magnetic field produced by a current carrying straight wire, a current carrying wire that is straight, depends on the we can say that it depends on the distance from it. The distance from it, how much distance it is, on that it depends. And every wire that is carrying current, will give rise to magnetic field. It will give rise to magnetic field that is carrying current, that will give rise to magnetic fields. So by using right hand thumb rule, we can say by using right hand thumb rule, we can say whether every place of current wire, every place of wire is using magnetic field or not. It is using or not, we can say it easily. Only the circular coil having magnetic field. If a circular coil, see a coil in circular shape coil having in magnetic field, if it has a magnetic field, if the circular coil has magnetic field, not, if it is having turns, then it turns, then it produce, if it is doing having turns, then it produces number of magnetic fields, that produces when it turns. Magnetic fields due to current. So what are magnetic fields due to current in a solenoid? Solenoid. Magnetic field in a current due to solenoid. A coil. So what is solenoid means? A coil that is a coil of many electric insulated turns. Turns that is wrapped with many insulated turns in a copper wire, and that is wrapped tightly and in a cylindrical shape. If it is in cylinder shape, then it is called as solenoid. Then it is called as solenoid. Then it is called as solenoid. Solenoid. So here see a coil. One minute. Here it became 1 minute. A coil. See here, a coil has one end of solenoid solenoid act as north pole and other as south pole, and other end act as south pole. It acts strong magnetic field in a solenoid. If we get strong magnetic field in a solenoid, then we can use it as magnet. If we get the magnet is called as electromagnet. It is called as electromagnet. A strong magnetic field in a solenoid which can be used as magnet is called as electromagnet. So this was about solenoid.